All right, hi everyone. I'm Shaylee Valentine. I created these R workshop materials so folks can have them freely available and be able to learn how to use R for data wrangling and visualization and other typical projects and things like that. This is an introduction to basic R to learn what the R environment is and learn what R is all about, as well as some links to get help with it if you are interested. So if you are not familiar with R, I would start here. But if you are familiar with R, I would move on to a different tutorial. So this is basic R practice. I will be going through this R Markdown document to show what the R Studio console looks like and some basic coding in R. So as an introduction, R is an open source free program that's relatively user-friendly because so many people use it and post the open source code, and it's free. So we recommend using R, as in me and my colleagues, no matter how simple it may seem for your analysis, like calculating a mean or sorting your data or basic visualization, because having the code written out means that any analysis is reproducible for yourself and for everyone else. While in Excel, you might not remember what you did, or in another click button type statistical program like SPSS or something, you are just clicking those buttons. So it's not as reproducible. It might be more difficult or time consuming to learn R for something you know how to do in Excel or can learn slightly faster in Excel, like pivot tables. But your data, your analysis will always be reproducible in R rather than Excel. So learning how to code in R, learning this language will be really beneficial for making your code, for making your data much more transparent when you go to do research. So today I'm going to briefly describe some of the very basic R functions that can be helpful just to get you started with R and learn the layout of R itself. And I want to note, like I mentioned at the very beginning, this is an R Markdown document, which differs from an R script. So most people use R scripts. Anything that's not commented out with a pound sign is code in an R script. In an R Markdown document, people use it to make things like PDFs, HTML files, so you can actually type text, which all of this is. And then there are specific code chunks to put code into. So if you are interested in learning Markdown, I have another module or tutorial that goes into a little bit of the basics of R Markdown and how to format for it. So there are a few books I recommend for learning R at the get-go. For just getting started with R, that's all, you're just trying to get an introduction. I would recommend getting started with R, An Introduction for Biologists by Annie Beckerman, Dylan Child, and Owen Pecci. If you want to learn tidyverse and data manipulation techniques, I would recommend this R for Data Science book by Hadley Wickham and Garrett Grollman. There's a free version online for the second edition, so I would just start there. This book is very helpful for me to learn how to use tidyverse functions, which I would highly recommend over base R functions. But do as you want with this and see if you're interested in that moving forward. All right, first to get started with R, we're going to talk about annotating code. And this is that pound sign for commenting out code or annotations that I mentioned. So when you write in an R script or a code chunk in an R Markdown document, you really want to annotate that code. Always annotate your code, which means you have to comment out the code. Everything written in that R script will run because it is read as code by the computer, unless you use specific arguments or comment out the code using that pound sign. Your text changes color too when things are commented out, so it's really easy to distinguish your code from your comments. But why should you heavily annotate your code? What's the point of annotations? What do these actually mean? These annotations, if you do them as you probably should, is to say what your code is doing. So, because unless you consistently use R and the same exact functions in R all the time, you're not going to remember what that code does a week, a month, a year from now. So, annotating it to say, this is what exactly this code is doing, these are the arguments within this function, this is what it needs, will really help you later on so you don't have to relearn that material so much. So, annotating this code can help you pick it up again after you have that break. Annotating code also makes it easier for a collaborator, advisor, journal reviewer, etc., to see what you did with your data and make sure the data analyses were appropriate for your data sets. If you want to manage your data wrangling, management, and visualization process, the easiest way to do this is explicitly state what each line of code does to your data set. Now, if it's like a common type of function, once you get used to R, I wouldn't comment that out to say explicitly what if it's doing like a filter function or something. But as you are learning R, commenting it out will and annotating it in this way to tell you what this is doing will really help you also learn how to code better, faster. So in our markdown documents, we have these code chunks, which are 3 tick marks on each side, and you can name the code chunk. So we could name this like comments, for example, and then they'll have some arguments there if you want. This is not commented out code. So if we were to run this code chunk, this first line will run because it's not commented out. And we get this error because it's not actually a function. It doesn't make any sense. Unexpected symbol in this will because it's not actually a function here. This will not run because it is commented out. So you could run that and it's not going to do anything with this part because it's commented out, and this is what your annotation should look like. With the theme I'm using, all code is in white, annotations are in purple. Okay, so that's the basics of like annotations versus code specifically in these code chunks or R script or whatever. If you weren't in an R Markdown document, the whole document for an R script would be basically a code chunk. So just use the pound sign to comment out any annotations there. All right, now we need to talk about the windows in R. So there's 4 different windows that are open and they have multiple tabs. This window, which is the top left, is your coding window. Your R script, your R Markdown file, whatever project you're using, you type code in here because this is a document that you can then save, which will then be saved on your desktop so you have your code permanently. I would only type code into this window so you can add things like code chunks and type code here. Only type code in that window specifically. You can also have multiple tabs open. So right now I have this tutorial. I also have other projects I've been working on as separate tabs here. So you can go back and forth within them. The window below this in the bottom left is the console. This is where code is shown and warnings whatnot after you run it. In an R script, all your code and its outputs will be in this console. In an R Markdown document, unless you switch to show code products in console, they're going to be after code chunks, and some will be in the console. So you can type code in here like looking for help, and it'll come up in the bottom right with help. You can type your code right directly in here. and get products just fine from that, but it's not going to save your code. And that's why it's important to type it into the coding window in the top left here. The window in the top right, the first tab is the environment. So any data or objects you have read into or created for that in that R session are shown here in your summary. It also gives like the size, observations, variables, etc. I don't have any data in right now because it shows that the environment is empty. You can click on the history tab as well to see what functions you recently used. So we recently tried to run this full run because it's not commented out twice, and also a help function. So that's a history of other things. There's connections and a few other tabs up here, version history and stuff like that. The environment and maybe history are probably the two you will most frequently use. The window in the bottom right has a lot of tabs in it as well. So this one came up with a help file because we searched for help. The files, we'll start with the files tab here instead of the help tab. The files tab shows you the files you recently opened in R or ones that are in your what's called your working directory or where R will save your files. And you can click on them to bring them in. So we could bring in the R Markdown tutorial and I'll open up that file directly. So that's a different tutorial. There is a plots window where if you make a visualization, it would show up here in R script, or if you run it in the console, it'll show up here and you can export and zoom in on your plot. There's a packages tab that shows you all of the packages you have downloaded for R. These are things that contain different functions like ggplot to bank visualizations, GLM to do linear modeling, those kinds of things, and you will have to attach these packages to use them each time. There's a help tab that you can search for topics such as like ggplot, and it'll show you search results. It'll give you vignettes, it'll give you code demonstrations, help pages for different packages or different functions as well. I don't really know too much what viewer does or presentation. I have not used those tabs, but if you are interested, you could explore them further. I want to note that when you run code in an R Markdown document, it differs from running code in the R script document. So when you run code in this R Markdown document, the output is shown below each code chunk in the coding window, so in this window. When you run code in R script, the output is shown in this console in the bottom left. And then the plots and figures are in the plots tab on the bottom right. So that is the difference here, or one of the big differences between R Markdown and R scripts. Okay, so those are the major coding windows and other windows in here where you'll find your data. So we're going to look at getting help next. So inevitably in R, I do this all the time. I always search for things. You won't be able to figure out a function, and it's frustrating, but you can always find help. So you can actually code this. So you can try something like question mark and your function name, or help in your function name within parentheses, where the function is whatever function you're trying to use. So for example, if we wanted to look up the mean, question mark mean here, and it'll come up with the mean from base R package in this help window. And it'll tell you, okay, this is the function mean. These are the arguments in each of that, for each of that functions, within that function, I mean. So X is an R object. Trim, observations you're trimming, removing NAs, etc. It'll give you some information, a reference for this, and also examples for how to use this function. Help with mean here does the same exact thing. it comes up with that again. It's just two different ways to code the same information. And that's what we'll find in R is that you can get the answer from many different ways, the same answer from many different ways using different functions. So this is the basic help function. You can also just search in the viewer or the help window here in this little search and look for mean, and it'll also come up. So there's three different ways to look for that. So in the bottom right window, the documentation for the function will pop up and has that information that we just went through scrolling here. If you don't get anything to come up for a function, you may have typed it incorrectly, or you don't know what the function is called, or you don't have a package with that function. So you can try question mark function or help.search function. Like if we knew about the function aggregate, but we didn't have it come up for a question mark, we could do question mark, aggregate, and it's going to give us a few different help pages. Are you looking for in this package data table? Looking at aggregation for data tables. How about dbplyr, creating an SQL translator? What one of these aggregate functions or varieties of aggregate are you looking for? So there's a lot of different ones. And the same thing will be help.search aggregate. So this be a character string. There you go. Put that in quotation marks. And it'll come up with the same exact thing. So these two code lines will get you the same information there. You may also just want to look up an entire package to get help with it. So if we are going to learn ggplot, for example, or tidyverse package, we might want to say, we want to just look up the entire package. So help package equals tidyverse, and that's in quotation marks. So then it'll come up in this help window of easily install and load the tidyverse and the documentation for it with help pages or what to look at. So you can look at the entire description of this package, news, guides, vignettes, get a lot of help with that. And you can even search the R website directly from the R console using R site search with whatever you're trying to do in this in quotation marks here. And this will pop up in your browser from the R website. So we put in clean data, and there's R clean data, R get clean data, phylogenetic data, etc. There are a lot of searches that will pop up in that instance. And then, of course, you can just Google whatever you want or use any search engine you are familiar with. So things like Stack Exchange or other coding forums are really helpful for learning how to use the packages. You don't have to search for these things in R, but it can be really helpful too. But just Google it if that's more comfortable with what you're interested in. Okay, we've talked about this term packages. So packages are things or functions and sometimes data that people have created and are separate from base R, which is the defaults loading into R. To look at what packages you have, again, go to this packages tab in the bottom right, and it'll show you all of your packages. So this is what's called your library. Every package you've installed, so you've downloaded it from R or GitHub or wherever else, will be here. And when you start up R, you need to load the packages you want to use because they contain different functions and they're not all automatically loaded. So what you can do is you can click on them, like maybe you want to include library abind, user library, this package abind, and we'll notice that in the console it popped up with this code library parenthesis abind. That's the code you would write if you wanted to code it, just like we have here of load package dplyr, and we can run that and it'll load the package. The other option is to just click on them here. But I would recommend writing them in code because then you can just quick run the code every time you open the document. And it'll be clear to reviewers, to other folks, which packages you are specifically using. If you don't already have a package installed, you will have to install it before you can use it. So you have to either click on install in the packages tab. So this button that says install, and it'll come up with a pop-up window. Install from where? Usually the repository. You can type in a package. It'll give you examples of or guesses to which ones. So you could click on like install tidyverse there, for example. And you usually want to keep install dependencies there. And you can select your library, which I just have one default library for mine. This is already installed here, so I'm not going to do it, but if you needed to install tidyverse, you could just hit install. Otherwise, you can use code. So it's just install.packages for the function. And then in quotation marks within these parentheses, you will want to put the package name. So here, dplyr, you could do tidyverse, whichever ones you want. So this is the package you desire. Here, install it, run that code. I do want to point out that on all of these packages people are making, some of them will have the same function name within the package, but the functions do completely different things. So I notice this a lot when I'm doing geospatial analysis, when I'm using the tidyverse functions. So there's things like you can filter using the filter function normally, or you can filter using spatial objects, or you can filter multiple ways. Or in other instances, multiple packages will have the function summarize. You want a summary of your data. So when you have multiple packages loaded, especially for when we talk about dplyr, if you look at the data wrangling tutorials, it often needs to be specified that it comes from the dplyr package and not a different package, because summarize is a very common function name. So if this is a problem where you're like, I know what I'm doing with this code, why is it giving me an error? Why is it not producing the output I know it should be doing? You should specify the function. So let's say we want to use the filter function from package SP, which is a spatial package, rather than the base R filter function, or the dplyr filter function. Here, specify the package name, 2 colons, and then the function name and whatever arguments you have for that function. But if you need to specify because you're coming up with issues, it's the package name and these 2 colons followed by your function name. And that'll get you the correct package function. As an aside for that, it will come up in later tutorials. Okay, so your working directory. Your working directory is where R is getting documents, data, everything else from, and saving things too. When you install R, it will make a default working directory, which a lot of times are like your documents folder. And that would be the directory that everything is stored in. Every time you open R, that's what it'll go to. And sometimes you don't want to load in data from that working directory, or you want a different working directory to save to. You can longhand write out the file path name or set the working directory to what you want. So those file path names, if you're using things like Microsoft, file path name are basically what's up here. The C users, Valentine.474, etc. is your file path name to this information. You can put that in here and we'll show that. And you can figure out what your current working directory is using this get WD for get working directory. It'll tell R to look for that working directory, which right now it is in the Valentine Hood class week 1 R basics working directory. So it's pulling information from this R basics file folder. I could reset my working directory, for example, to my desktop using the setwd function for set working directory. Set working directory, and that's a long file path name for the desktop, as in desktop here. In R Markdown, it'll give you this warning that the working directory has changed to the desktop. But it'll only be changed for this specific code chunk. So if you want to change it for the whole session, you have to do something else for R Markdown documents. For an R script, it will change it for the whole time your code is open and R is open for that R script. So yeah, just ignore the warning for this right now because it's an R Markdown document. I do want to point out that when you are specifying a working directory through code, these are forward slashes rather than backslashes. So Windows, at least, I'm not sure about Macs or Linux, but Windows will have backslashes in your file path, and you need to change them to forward slashes here. Okay. So there's one more way to change your working directory. The issue with working directories in R Markdown, again, is that they only change for the one code chunk. So remember that in our Markdown document, it's much easier to change the working directory using the Session tab at the top. Here, Session. And then you will go to Set Working Directory. You can choose the directory. It'll pop up and you can search and say, I want to choose my desktop. And it'll change it for the entire R session, which is until you exit out of R in RStudio. You can also do session, set working directory to source file locations. So wherever this file is saved, and I'm not sure what to file's pane location is, you could play around with that if you want. But that is how you change it more easily than setting the working directory this way. And again, once you change the working directory, it only lasts for that R session. So until you close out of R, which might be easier to just set the working directory if you're going to be opening and closing this document a lot using code. All right, so now we know a little bit about R. Let's talk about loading data. So you're going to need to load external files and save those that you've made in R. The biggest thing is do not load in XLS or other types of, quote, normal Excel files. Things usually get messed up, and I think R has improved on this front, but there's still a lot of issues. I would always convert XLS files to CSV file in Excel before loading it into R. It'll save you a lot of headache long term down the road when you have issues with the XLS files. So always bring in a CSV if you can. To load data. If your working directory is set to where your data is located, you can just read those data in using this function read.csv, for example. We have a data set called stream solutes, and the extension is .csv. So that extension always has to be there for a file, and the name must be in quotation marks. So if this is in the same folder as where this document is saved, we can run this code. This arrow means save this function read.csv, so it's reading in the data. Save it as an object called species. This object will now appear in your environment in the top right, where our species data is. And we can see it's 29,261 observations, so that's the number of rows, 9 variables, which is 9 different columns. So we can see that This makes this is exactly what that information is here, and we can see what variables are in there, their names, what the columns actually look like, what the rows look like. A species wasn't an appropriate name for this because it's a stream solutes data set, but you can literally name these anything you want. Stream solutes, it'll read it in again as a different name. Whatever you want to name it, you can read it in that way. If you didn't set your working directory, or you only need to bring in the data from one other place that's safe somewhere else on your computer in a completely different working directory, you can specify the long file path name. Remember, it's forward slashes instead of backslashes to wherever that file was saved. So you have the file path all the way here, and then the name of that data set, streamsolutes.csv. We'll read it in a species. It's the same exact data set that we're reading in, but just multiple different ways of doing it. And instead of your data being saved in the same location as our markdown document, maybe you have a subfolder called data or something like that, and you can still read it in from that subfolder. So to read it in from a subfolder, this period here indicates that we are looking in the same or file path name as where this document is saved. And then it's forward slash, and then it's a data subfolder forward slash, this is the document name, stream solutes, and this will read it in because this data set is in multiple locations within this within these folders, just for examples. So these are all CSV files, but a lot of us have things like TIFF files or shape files or text files as well. You can read in so many different file extension types within R. Just, again, don't really do Excel ones. Just don't load them in XLS files because there will be issues later on. So for example, we can read in shape files using library SF. I have to load that library. And it's a read underscore SF. Here it's saved in our subfolder called data. It's called TNC terrestrial ecoregions.shape. That'll read in. It gives me an error because cannot open, so it might be named something different. I'll have to look at that later, but that's how you would read in a shape file. For a table, it's read.table. And you specify your path. So within the same folder as this document, within the data subfolder, and our monthly data here. And we're saving it as an object named table. It gives an error because this line did not have 13 elements. So if we look at our data set, we got data here. We open up this text file. You might get issues with text file because this has like a weird header at the top. So you can say header equals true or something for that text file to open. So let's see if that works. We could look for read.table and get help with this function. The default here, if we open up to the help page, is header equals false. So we can add this argument that header equals true for us because we open that. More columns than column names. This might just be an issue with this data set, and I would have to look at this further to know what's going on, but that is actually how you read the text files in. This might be something that's different with these text files. The issue with this shape file, if we look at this, is that it's only the .shp file here. And when you produce a shape file, there's a whole bunch of other files with it, like .dbf, everything else. And those files must all be together for it to read in the shape file because that's where other information is stored. So if you just have this .shape only in your working directory, it won't read in a shape file. but this code is right. Our data are not in the right format for it right now. So there's a lot more that you can import data types. So check out this tutorial on how to import files. Just click on this link if you're in the HTML, or just copy and paste this. All right, so I mentioned objects where we saved the data as an object name, so like stream solute species here. You can also create objects in R, and these are just basically just giving names to your data, giving names to numbers, giving names to your data frames that you're manipulating in R, and then you can call on them later. So what you have to have a name for it, the arrow sign, which means a sign, and then whatever you're assigning to that. So here we're creating an object called banana that contains a value 1. So all we have is 1, and we're making banana equal to 1. So we can run that code, and it'll pop up in our environment as a value. We have banana 1. And then we can call that object, so call banana, to see what it contains in the future. It just has 1 in there. So here we assign the value 1 to the object banana. And you can directly use this object in functions now. So we can say the sum, calculate the sum of our object banana, which is 1 because it's one number. Same with mean, mean of 1 is 1. So this isn't exciting with just one number, but what we can do is create more numbers now here. So this is a vector of values using this C or concatenate function. This is a really helpful function, and we'll see it a lot more often in other modules too. But this essentially says just group all these numbers together. So C, 1, 2, 3, 4, 5. Concatenate and name it object orange. So now in our environment, we have orange, and then we have it as a numbered variable 1 through 5, and we can see that's 1, 2, 3, 4, 5. Exactly what we called it. We call orange here, gives us our numbers we input. Now we can do a sum of this. So literally just put in your object name, because it's just one column vector here, sum of orange. 15, it's adding up all those numbers. And we can get a mean, which is going to be 3. The average of 1 through 5 is 3. So that's really easy ways of looking at objects, and that they are storing information that then you can perform other functions on. Mode and class. So objects have a mode and class, which can give you a lot of information about what's in that object. So class determines how functions act on the data, and mode is the overlying structure of the object. A lot of times they are very similar to one another, but sometimes they can differ, and it can give you errors, and it's really weird. But sometimes you might have to look at mode and class. You can also coerce both into something else. So for example, object orange, or 1 through 5, is class. We'll just say class as the function, put our object in there, is class numeric. And our mode is also numeric. So both class and mode are the same thing. We can change the class of the orange to a data frame, which changes the mode as well. So this is coercing our data into a different class, because it's just numeric right now. Maybe we want it to be a data frame, just like species and stream solutes are here. So we say data.frame. It's a way to coerce it as the function, our object orange. We're saving over our orange to change it. Now our orange moves from values, which were numeric in our environment here, to data. We have made it a data frame, so it moves up within the environment. If we run class orange, it's called a data frame. That's what we named, or that's what we coerced it as. And if we look at mode, it's now a list instead of numeric. This coercion is helpful when you're trying to use different functions because certain functions will need things like a tibble, a data frame, a list, a vector, numeric only. So you might have to coerce this stuff in the future or create things like empty data frames to put values in or change things like that. It also works for just coercing part of the data, so not the whole object itself. So we're going to use the trees data set for this, which is a data set inherent in R. So to call it, you just say data trees. Here, it went from values to data, and we can look at this, and it's a girth, height, and volume of 31 different trees. And if you search the trees data set, it'll come up in the help window to give you a description of what these actually are, which is the diameter, height, and volume for black cherry trees. And it'll give you information on that. All right, we can look at the structure of trees. So this is another handy function to look at our data sets, str. And if we go down to the bottom of this code, we can see it's a data frame, 31 observations, 3 variables. And it'll give you those variable names of girth, height, volume. It'll say each one of these is numeric. And it'll give you some of the values. What's important to note here is this $sign. So the data frame is called trees. It has variables girth. This $sign here is how you get at those variables in different functions. So we'll see what that looks like. All right. For some reason, maybe we want the girth value to not be numeric. Remember, that is numeric down here. Maybe we want it to be a factor, so it's like categorical or something. We can coerce it using this as.factor function. If we want to just change girth specifically, we call the name of the data set, which is trees. That $sign, that was important, girth. This right here, the trees, $sign girth, will just give us the girth variable. Those are the girth data. So we're saying change girth and also write over girth. So make it a factor. And you just say write over it by saying trees data set $sign variable girth. Same thing here. That's how you write over a variable. So then if we look at the structure of the data again, girth now is a factor, not numeric anymore because we changed it using that as.factor function. And it says it has 27 levels. So there are 27 different values for girth. Cool. So we made it a factor. We can also make girth numeric again using a double wrapper. So this is something that comes up a lot. So sometimes your data, if it has NAs in it, and it's a numeric variable like weight, length, or something like that, and you read it in and it has NAs in it, R is going to call it a character or a factor when you want it to be a number. The issue with just treating it as numeric and just doing a as.numeric value is R is going to rank your factors then. It's not going to give you the exact number that was there. It's going to give you the rank, and we're going to see that in a moment. But if you need to convert from a factor or character to numeric, it is this double wrapper of as.numeric parenthesis as.character with the name of the factor or character variable, and write over that trees girth again. And if we look, trees girth again is numeric, and it's the same values it originally was, 8.3, 8.6, 8.8, etc. All right, but what if we didn't use those two variables? It's going to rank the data. So here we're just going to save trees as trees1. And it's the same data set, it's just saving it over so we can compare the two. Trees1 girth. We're writing over that with trees1 girth. Calling it a factor, this is exactly what we did earlier. So we're just made it a factor again instead of numeric. And if we do that as dot numeric function on our tree's girth rather than as dot numeric as dot character, just this function. And if we look at these data, it tells us 1, 2, 3, etc., 1 through 27. Because some of them have the same girths. There's 2 14s, for example. Because it ranked the data. We look at the original data. This is the smallest individual, so that's going to be number 1. The largest is going to be the last number, 27. It's not going to give you the actual variable names. So what it does is R just ranks your data 1, 2, 3, 4, etc. So this is something to keep in mind, and it will come up in the future. All right, now we want to view our data, and there's multiple different ways of doing this. So after you import your data, your species, your stream solutes, your trees, you always want to look at it to make sure it read incorrectly. And you want to check on that data throughout data manipulations, wrangling, tidying, etc. So glance at it periodically. So for this, again, we're going to use the trees data set to look at the data in the following ways. There's many different ways of looking at your data. Head, function head shows the first 6 rows of data. So it's just head with your data set in there in trees. It's first 6 rows, we've got girth, height, and volume there. We could also do this with our stream solutes. And it'll show you the first 6 rows and all of the data. Tail shows you the last 6 rows. Make sure your data look fine on the end side of things. Dim gives you the dimensions, rows by columns. So it's just Tim, and then your data set, trees, 31 rows, 3 columns. That's exactly what we see. 31 rows here, 3 columns. So names gives you the column headers. This one is very helpful because R is case sensitive and spelling sensitive. You will need the same exact spelling and capitalization in your data wrangling. So it's just names in your data, girth, height, and volume. You can also just copy and paste these and put them into different functions. View opens the entire data in a new tab, and that's capital V, view. All right, just open the data set in a new tab. It is the same exact thing as clicking on your data in the environment, or to open up a new tab for that. N row gives the number of rows, and N col gives the number of columns. So N row trees, 31, and col trees should be 3. Yep, 3. LS gives a list of all the data files in the global environment. So in your environment up there, so it's a list of them all. So we got banana, starts with the values. Orange, species, stream solids, trees, trees1, etc. It's alphabetical order here. What you'll see in a lot of information on like changing parts of code, changing parts of data sets is this bracketed row column format. So this is base R, uses this row column format to denote columns and rows in most data set classes like tibble, matrix, data frame. If you're selecting different parts of your columns or rows, you can extract information this way, especially like model outputs like linear models. You can use this as well. So because it's row column, let's say our trees data set, and we say we want to view the 3rd row. So first part of comma is row. We're leaving column blank, so it's just going to give us the entire third row of data. Yep. Row number 3, girth, height, and volume variables. Our trees data set, we have it blank for the row and 1 for the column. So we want to view the first column of data. 1 column right there. And then if you want just one cell value, you can do the row and column. So going to give us the third row, first column data value is 8.8. Why wouldn't you just name maybe the row name for this, for looking at the column? And that might be because you have multiple data sets you're working in a for loop, or you're trying to just get a model output value. And so you need to call the column row or column number or row number to get those output values rather than state the name of a column or state the name of a row every time. All right. Object $column allows you to specify a available column from the data set, just like we had looked at. So trees $girth gives you that girth column. You can put this into functions like we were seeing with the as.numeric, as.factor, etc., changing that. But you can do it with any other function too. So if we wanted to get the mean of the tree girth, we say mean, specify your data set, $, means go into this column called girth and calculate the mean, 13.24 centimeters. Okay. A lot of times when you're first learning R, especially for people who use base R when they're teaching, they'll teach you how to attach your data. Normally in R, you have to specify which data set you're working for and any code to run properly. So like here, we specified the trees data set. And we said go into the girth column in this trees data set. We could specify then later, look at the mean of stream solutes. And what's nice about RStudio is that if you do the $, it'll come up with all the column names, so you can just click on one if you wanted. And we can get milligrams per liter, the mean of that in the solutes data set. So you can specify any data set using this. The attach function that you may be presented with, it tells R to exclusively work in this data set only. So you don't have to use the object $column notation. However, using attach leads to many errors long term because you might be looking at multiple data sets, combining data sets, doing a lot of different things. Therefore, this information is there for you to know how to attach and detach because it is widely available information, but I do not recommend using attach or detach because it leads to errors in the future. So again, here's an example of not attaching the data. Let's make a histogram of the girth variable within the trees data set. Specify the data set $girth. I just made a quick, easy histogram here. Here, what if we just were like, we want the girth variable, so hist girth. Nothing's going to happen, but it says object girth not found. It's looking specifically for an object, which would be in your environment. There's no girth object there. But if you attach the dataset trees, attach, you can run hist girth because it is telling R, go to this data set. So it might save you time from typing out trees $girth, but it will lead into a lot of problems in the future. And if you need to detach the data to work on another data set, you have to say detach trees. So this can lead to a lot of errors, but it's here for your information because it is widely available. When we start using tidyverse functions, we're going to be using something called the pipe, which is also now in base R2. That is much more beneficial than attaching, detaching data objects. And you likely not use attach or detach if you currently use it once you become more comfortable with programming in R. So if you don't know these, I would not look into them. I would not use attach and detach. And if you are using them, I would wean yourself off of them. One of the most important parts of R is to have repeatability and reproducibility. So sometimes when you're running models or doing like random number generators, you need to repeat that sequence. So you can use something called a seed to repeat the sequence of random numbers or random modeling. And it's this function set seed. So set.seed 126. Let's say we want to get 5 random numbers, which is just random norm 5. So we run this code. The seed can be like anything you want it to be. I just have 3 numbers here, 1, 2, and 6. It gives us 3 random numbers between 0 and 1, or between -1 and 1 here. If we wanted to create these same random numbers again, we say set seed with the same sequence, 126, and I'll do our random numbers again, and it gives us the same exact numbers. If we set a new seed to be 7, when we're generating 10 numbers, we get 10 different numbers than our 126, and we can repeat again, get those same numbers. So this is just a way for repeatability, and it can be a lot more complicated than this with your modeling outputs. But this is just an example of repeatability. Set a seed for that if you are interested. And then finally, we want to save information. So we want to save data that we made in R as a CSV, as a text file, whatever, as a shape file, as a TIFF file, PNG, etc. Now you want to write a CSV file in R. You made a data frame, for example, and you want to save it. It's just the function write.csv. Specify the name of the object and the name you are saving it as. So what we could do is say write.csv, the trees one object, and we could say this is trees data.csv. Always have a file extension. Run this code, and it'll save it in your working directory. So now we have this trees data set in our working directory that we just saved. And we can open it up in Excel. We can open it up back in R. But it is the trees data set that was inherent in R. It'll always spit out this row number column here, so you can delete that if you want. And for something like writing a table, it's write.table, the name of that table, and then it's my table.text. So you'd be saving a table as a .text file. And then finally, saving your work you did. Most students try to revisit an R script or R markdown file, and they have to punch through code when you open it up to get where you left off last, which is fine. You can do that in R markdown. You can also click on these buttons like run all code chunks above, and it's going to run through. If you're kind of messy with learning how to use R, if things are out of order, if you don't have all the packages loaded, if you missed some code in saving it in this coding window and put it in the console instead, it's going to create some chaos when you try to run that code. When you open R, it'll be an empty environment unless you save your environment. Sometimes when you close out of R, it'll ask you if you want to save your workspace, and you can click yes. It'll save your environment here with all your objects you made. What you can also do easily is save.image, And you can name this, put this in your working directory, name this as like whatever you want to save it as. Week one module basics practice.r data. This .r data extension is important. So if you save it, it'll save an R file that has all the information that we worked on today. And then next time you open up your R file, you can say load and provide the name of your saved image or saved environment, saved code space, etc. And it'll load that environment back up so you don't have to run that code again. Everything's available to you. So with that, this is the end of the basic R tutorial. It covered a lot of things like what R is, what R studio windows there are, some basic coding functions that will be helpful moving forward, what objects are, how to search for help, what a function is, what packages are, how to reproduce your data sets using seeds, and then reading in and writing data, as well as saving your R data here. So always open to feedback. Let me know if there's anything else that should be covered.